Good morning. Okay, so we will continue. First of all, I would like to revise what I say from the last lecture. So, last lecture we have been talking about like the different, like the concentration in the metal semiconductor, this kind of the Schottky rectifier, and we have been discussed that the impact comes from the concentration. So if you look at this equation, so it's indeed that once the concentration increase, our depletion width should decrease. But actually, this also will increase as well. So the concentration will be also increased. And therefore, the E max here in the end should be increased. But however, why our breakdown voltage usually will be lower? This is because the breakdown voltage is usually often triggered by the E max should be smaller than our critical electric field for the one specific semiconductor. For example, that's how we call this as a E critical. So that depends on the different material we have, the different critical electric field. That's a maximum breakdown strength for the one semiconductor material. So usually we have the one specific for the silicon that can be certain value, but if you have other material that can be related to other value. So in anyhow, we need to make sure our E max should be always smaller than the E critical. But however, if the E max is larger than this one, if E max is larger than this one, then we will start to trigger for the breakdown. So if our E max is larger than E critical, then usually we will trigger the breakdown for one semiconductor device. And that's why that the one with a higher concentration, we always have a lower breakdown voltage, because right now the higher concentration here, so let's say this one is increased, and therefore the E max in the one in the specific Schottky semiconductor junction, the electric field in the Schottky semiconductor junction should be increased as well, and this one has a chance to larger than E critical. So that means with a smaller amount of the voltage, the E max already larger than the E critical. So that's we have the early breakdown. We will have the early breakdown here. So that's the reason why the higher concentration always has a lower breakdown voltage. This is because the electric field is higher, and then it's higher, is higher than our critical electric field. Okay, so this is some more comment from the last lectures. Okay, now we'll move to another type of contact, which is usually we call this as ohmic contact. And the ohmic contact is non-rectifying barriers. So ohmic contact are metal semiconductor contact, but in the case they are not rectifying anymore. So that means this will be the case of when whatever you apply the current however you apply the voltage, it will always have the linear correlation between your voltage and then the current here. And an ohmic contact is a low resistance junction. So it's a low resistor junction that's providing conduction in both directions between the metal and the semiconductor here. So it should be have the characteristic like in this way. So we have the current versus voltage right now, because it's a low resistance junction. So we will have the linear correlation between the current and also the voltage, and the slope here is our resistance. And also we have the ideal ohmic contact should have very low resistance. So that means we should have very steep IV curve where our resistance is as lower as possible we want. So usually when we make the ohmic contact, we always want to have a lower resistance here. And the reason why have the ohmic contact is because of the metal work function, the correlation between the metal work function and then also the service potential. So now if we assume in the case where our phi n is smaller than phi s, as usual, so the left hand side is our metal, and then the right hand side is our n-type semiconductor. And then in the left hand side, we have the metal work function. So that's EF, and we refer to the certain place, and therefore we have a phi n here. And in the right hand side, we also, since this is a n-type semiconductor, so we have a EC and EV. And since this is an n-type semiconductor, therefore our EF is close to our conduction band. So our EF is close to our conduction band, and therefore we have several parameters here. So one is electron affinity, and also another one is E phi s. So this is a case where our phi m is smaller than our phi s, and therefore the band diagram, the band diagram that we haven't connect the metal and then the semiconductor is shown here. And once we connect it, for sure, first of all, our Fermi energy will be the constant through the system. So that's EF here. And right now, then the banding is start changing. So we have the conduction band here. And because right now we try to align this with this. So this will be connected as a constant, and therefore we can expect the band bending like in this way. And right now our phi m, this is our phi n, and this is our so right now we have this one. So this is our Fermi energy, and this will be equal to our phi n. So to achieve thermal equilibrium in this junction, electrons flow from metal into the low energy state in the semiconductor, which makes the surface of the semiconductor become more like the N-type here. So that will be more become more N-type, because right now in this surface our Fermi energy is already above our conduction band. So that means this place has a very higher concentration. It's like the N++ region. So that's why we won't have any barrier in between the metal and then the semiconductor. So that's why we will have this kind of ohmic contact characteristic. So similarly, we can consider another case where this is for the p-type. That is the p-type. When we have a p-type semiconductor, if we want to make as ohmic contact, then our phi n should be larger than phi s. So our EF is close to the valence band, and this is phi s. So right now phi n is larger than phi s, so that means our phi n could be somewhere here. So this is case phi n is larger than the phi s here. So once we connect this junction, then as usual, we first of all and our Fermi energy is constant through the system. And so very similar to our N-type case, right now the surface here is become more p-type. So that's like very similar to the case of a p++. So our this is our here. Our barrier is equal to here phi p. So this is a case where the ohmic contact formations in the p-type semiconductor. So then if we want to make the ohmic contact in p-type semiconductor, we need to make sure that we have to choose the metal where our metal work function is larger than our phi s. And in the case of a N-type, we have to choose our metal work function smaller than our phi s. And there's also one very interesting barrier that we call as a tunneling barrier. So the tunneling barrier is the idea that the space charge width in the rectified metal semiconductor is inversely proportional to the square root of the semiconductor doping. So as you know, the concentration is increased, then depletion width is decreased. That's as a saying here, the space charge width is inversely proportional to the square root of the semiconductor doping. The width of the depletion region decreases as the doping concentration in the semiconductor increase. Therefore, once the doping increases, the probability of tunneling through the barrier is increased as well. So this is a case to illustrate. This is N-type semiconductor, and this is N++, right? Because this Fermi energy is close to our conduction band, so we can consider this is N++. And because we consider that's N++, and therefore the depletion width here is very narrow. The depletion width is very narrow. And once we have a narrow depletion width, there's a chance that the electron is able to tunnel it through the barrier here. Even it didn't have the exactly ohmic contact characteristic, it still have the barrier height here. But because right now the barrier here, the depletion width is narrow, therefore the tunneling probability is increased. Therefore, the electron can start to jump from here to here or here to here. And therefore, that's still possible to have the current conduction. So that's why we call this as a tunneling barrier. That's why we call this as a tunneling barrier here. So sometimes, it's very often to see that we actually will prefer to make our source drain with a highly doped region. This is because we actually want to have the very low RC between the metal and semiconductor. So once we use a higher concentration, we expect the contact resistance is reduced. And one of the reasons, of course, sometimes we choose the certain work function to make it ohmic contact. And not only this, sometimes we also consider to use a very high concentration because we want to lower the RC. And one of the reasons is that it can form the tunneling barrier between the metal and semiconductor. Okay, so here's some of the certain theoretical calculation, but we won't derive here for you. You can look up by yourself. And the conclusion is that the contact resistance is correlated with phi BN, so that's a barrier height. and also the concentration. So the idea to design the good ohmic content, idea to design the low content resistance is usually we decrease our barrier. We have to find the metal that can decrease the barrier height, or either we increase the concentration. So in this case, we always can make sure that we can get very low RC as possible as we can. Okay, so let's look at some of the literature. You might be wondering, like this is ohmic content. It looks not that complicated because just consider the barrier height between the metal and semiconductor. But in some of the technology, actually is pretty important to continue try to optimize the characteristic between the metal and semiconductor. And of course, in the silicon world, this is not the issue. But right now, is the issue. Most of the issue for the other semiconductor material, like the 3-5, like the compound, like the 2D material. We're always suffering to have the good Schottky or ohmic content between this kind of the materials. So this is one literature to show you that what we have learned in this chapter is actually quite useful for us to understand like a certain knowledge in the published literature. So as you can see, the title of this paper is Schottky barrier and contact resistance. Of course, this is not in the gallium nitride, it's on the P-type of GaN. It's not in silicon, it's on the gallium nitride. And in the early days, people already found out that gallium nitride is a very promising materials. Not only for, in the beginning, it's used for the LED, for the lighting application, and later on for the power or RF. But anyhow, no matter for what kind of application in the LED or in the power or RF, it always suffer the issues that we need to have a good Schottky barrier height. We need to have a lower contact resistance in the certain doping gallium nitride material here. So this is a literature that published. Is already back to the 1996, but right now, nowadays, still very useful, because if you are in the field of a gallium nitride, you can understand how difficult to make the good ohmic contact on P-type GaN. That's still very challenging at this moment. So let's try to look at some practical case that have been published in literature. I believe that lots of the terms here is already mentioned in the previous lecture in this chapter here. So first of all, if we look at for the abstract, so we can try to understand what this paper will want to tell us. So this paper tells us that we measure Schottky barrier height and specific contact resistance for 4 different metal on P-type GaN. So from this chapter, we already know that the contact resistance of Schottky barrier height is highly related to the metal work function. So that means the different metals should have the different effect on our barrier height and contact resistance. And this is exactly how this paper trying to study. It just try to deposit the different metal and try to look at the Schottky barrier height and contact resistance here. And the Schottky barrier height, so in this paper, he tried to study the 4 different metal: PT, nickel, gold, and titanium. And these 4 metals still right now is very popular in our semiconductor industry, and were obtained from the current voltage characteristic. So you can see that the analysis here should be actually very simple. He's trying to extrapolate the Schottky barrier high from these four metal and based on the typical IV characteristic, and in the end he can obtain this kind of the barrier high. And also the next step is he want to extrapolate the specific contact resistance, which will be this here. So I think the title of this literature is already reflect what content could be in this paper. The title is mentioned. He tried to study the Schottky barrier high. He tried to study the contact resistance. And you can see the abstract. Right now, I think most of you here are the graduate students, so you should know how to read the literature, also how to write the academic writing. But you can see the abstract is actually very simple, because the abstract just try to reinforce the main point that come from, that indicate from the title, but we just put some more detail. The title is already mentioned, Schottky barrier. So therefore, when we try to write the abstract, it's definitely need to include the certain information related to the Schottky barrier. And when we have the title of a contact resistance, this also need to be mentioned in the abstract as well. So you can see that the abstract is not that complicated. Just try to write some more related to your title. In the end, it's always have the one sentence for the conclusion. So the conclusion is here. Our experimental results provide that Schottky barrier high and specific contact resistance decrease with increased metal work function as expected theoretically. So now you can see, actually, if you try to look at the abstract, what they say here is more or less very similar. In the beginning, he just said that we do the measurement in Schottky barrier high and contact resistance with a different metal, and this is a result, and this is a result. And then he make a conclusion that yes, our Schottky barrier high and then the ohmic, the contact resistance is decreased with increased metal work function. So I believe you actually follow, once you finish this chapter, it should be very easy for you guys to understand this literature. Even you have no idea about the gallium nitride, it's fine. But the terms here, especially in the abstract, the term here is nothing related to gallium nitride. It's just a very basic understanding related to contact resistance and Schottky barrier high. Okay, so let's look at, this is abstract, and then for sure we won't go very detailed. So let's look at this is a conclusion part. So conclusion part is basically just another refresh of our abstract, or another refresh of our introduction. So you can see the first sentence of conclusion. We measure the Schottky barrier heights of 4 different metals on p-type GaN. Now you see the sentence mentioned here is exactly the same meaning of the sentence that the first sentence in the abstract. So you can see that basically whenever you finish a conclusion or however you finish an abstract, you should already have the sentence in your mind to organize a conclusion or abstract, because these things should be very, very similar. So the first sentence exactly the same like this one. And also, by using the both large area contact and reverse bias IV characteristic, we also measure the specific contact resistance. And the conclusions here, it was found that the Schottky barrier high and the specific contact resistance decrease with the increase in metal work function. So now you see, these sentences are actually exactly the same. As mentioned in the abstract. So the conclusion, when we try to write the academic writing, you actually, what you have to remember is that our goal is not try to confuse our readers. Our goal is try to make things very clearly for our reader. So what we have to do is always re-illustrate everything again to reinforce the point, to mention the important points, and then we can try to deliver these important points to our reader and try to let them understand. And you have to understand that when you try to write the academic writing, we are not writing the novel, so we don't have to be write in the very suggestive way. We have to do the everything in the very straightforward, very open-minded, and very clearly that make our readers can understand clearly. If the readers can understand, if the reviewer, some of you here are the great the PhD students, so one of the PhD students, the most important job for PhD students is definitely to write the paper, but also the most difficult part is to write the reply to address the reviewer's concern. And most of the time, the reviewer has a concern is because the reviewer cannot understand clearly. So our goal is try to write our writing as simple as possible, as clearly as possible, and let the reviewer to be fully understand. Also, the last sentence is the same. The Schottky barrier heights are slightly affected by the metal work function. So now you can see the abstract and the conclusion, what they are trying to deliver are the very similar things that it's always related to this guy. They do the different experiments and then try to extrapolate the Schottky barrier height and contact resistance, and they found out that certain correlations. That's all. Right now, if you are not in the field of gallium nitride, that doesn't matter because so far we don't talk about gallium nitride here, but you already be able to understand the abstract and conclusion. And the most important thing is that even you don't look at the contents in detail, you already know that this literature is suitable for you. This is a literature whether you are looking for or not, because you already catch the key points here. So this is abstract, and then this is conclusion. Of course, after the abstract, we always have certain introduction. So this is a part related to introduction. And when we talk about introduction, there's definitely there will be the certain part which you mention here. It's related to the background introduction. So usually the background introduction is mainly related to why we have to study the gallium nitride, why the gallium nitride is good, and therefore we have to spend the efforts to understand the gallium nitride. So if you look at the detail here, it's mentioned the 3-5 nitride semiconductor are current interest in the viewpoint of application for the light emitting device. So this paper is mainly fabricated for the LED because of the direct wide band gap. And so that's a typical opening for the introduction. And usually the typical general opening, we will start to mention some recent work. So recently is some the terms that we use very often in the academic writing. So recently the p-type gallium nitride has been achieved by magnesium dope GaN, blah blah blah. So these are some of the details. In the end, the achievement of a P-type GaN has served a major breakthrough in 3-5 nitride semiconductor. So, to be honest, if you are not in the gallium nitride, this part is not really matter with you. This just related to the history, background related to gallium nitride. So when we try to write the introduction, there's always a part we just tell some of the history story. This just related to the history story to explain that how the gallium nitride is important for the semiconductor device. And these are also the same to also illustrate some of the history background. And usually the most important part, if you really need to look at the introduction, the most important part is always come from after the certain words. For example, on the other hand, or however. So usually this part is to illustrate that how good of gallium nitride, how like is a fantastic of the gallium nitride we can use. But however, or on the other hand, is usually to indicate that what we still need to address, what's the problem for this technology. And as you know, all of you here is trying to address the issue for your work, for your study. So therefore, once we see the on the other hand, or however, it's always related to our main key motivation in this work. So on the other hand, the measurement of a Schottky barrier high P-type GaN is difficult due to lack of low resistance ohmic contact required in the conventional IV method, which has been a major challenge to clarify the electrical property of the P-type GaN here. So now you can see all these sentences just mentioned that there's still so many challenges in the P-type GaN, and then we still face a lot of the difficulty to have the correct Schottky barrier high or ohmic contact resistance here. So here, the first one mentioned the one difficulty here, and this also to mention this as a one major difficulty in the P-GaN contact. So that's the point that after the on the other hand, or after however, we usually will start to clearly indicate that what actually the issues would be. And after this, usually we will have another term is called in this work that start to move on our main information, our main goal for that want to illustrate in this literature. So in this work, we systematically measure the Schottky barrier high of 4 different metals on P-type GaN. So now you see this one sentence actually is just another reference come from here, or another reference come from here. Actually it's just talking about the same things, that try to illustrate that in this world we just measure the IV on the P-type GaN with a different metal work function and try to extrapolate the Schottky barrier high and contact resistance here. So that's all. So this is usually the how we organize, how we try to write the introduction, abstract, and conclusion. But the most important is right now, you haven't started to look at IV curve yet. You haven't looked at any equation in this literature. This is a paper published in the Applied Physics later. So the Applied Physics later, sometimes we just call the APL. That's pretty well known in our domain, in semiconductor domain. If you get one APL, you almost like achieve 50% for your PhD graduation. So that's actually is a very good journal. But you can see, and also from the name of APL, you can expect this is a paper should be talking about lots of physics, should be probably include some of the physics-based equation. But right now in this page, we just quickly go through the abstract. We look at the introduction, we look at the conclusion. Even right now, you have no idea the figures inside. You have no idea their exactly the equation they use, but you already know the conclusion. That's actually the very important part. So when you look at when you start to do the paper survey, paper study, you don't have to look at everything detail. You should just quickly go through the abstract, introduction, conclusion. You can already know the main points, and then you can decide that whether you want to go for the details or not. And one thing, this is a background information, introduction, and usually after background introduction, this is part is more related to the motivation. So our motivation is try to address something that has been seen as a challenge, no matter for what kind of academics or what kind of a job, R&D job you are doing in the future. It's always to solve some issues. So this is the issues. So we need to solve it. So that's our motivation. And this is a way we try to solve it. Okay, so for sure we will still look at some of the a little bit detail for this paper. You can see that actually the equation showing here is not that difficult. It's just a very basic IV curve come from the Schottky contact, and also this is a curve you should be already pretty have a little bit sense, because this is a current versus a voltage, and if you try to plot in this way, you can try to make sure the Schottky very high. So that's all. So this is the APO paper. Probably the page of this paper is around like a 4 to 5 page, but now we use a 2 slide. You already can fully catch all the important things, and then you can decide whether this will be useful for you, or you can try to really look at the detail, like how this the paper can help you for your own research. Okay, so this is the last slide. So we'll start to move to the MOS transistor. So although we actually have been schematically draw, and we have already talked about the fundamentals part of the MOS, and also I believe you guys right now is already be familiar with what would be the MOSFET look like, but still there's some details we need to put some efforts in this chapter. So this is fundamentals for the Metal-Oxide. Metal-Oxide semiconductor field effect transistor. So that's why we call this as a MOSFET. So before we talk about MOSFET, we still want to put as a simple version of the MOSFET, where we want to focus on the MOS capacitance, because we believe the heart of the MOSFET is MOS capacitance. So the structure of a MOS capacitor is shown here. For sure, we always start from the certain substrate, but right now we don't have a source drain. We just put a certain dielectric on top of the silicon substrate, And the most often dielectric we use, which is the silicon dioxide. And there's two parameters we use very often to characterize this dielectric, which is first one is a dielectric constant. And also the second one is a dielectric thickness, Tx here. And after dielectric, we start to deposit our gate metal. So now you can see this is just a very simple structure for the MOS capacitors here. So we first starting from here, because once we understand the MOS cap, MOS capacitance, that can help us to understand the MOSFET. And the capacitance here can be calculated as shown here, which is related to your dielectric constant over your thickness. And this is equal to thickness. The D is a distance. That for sure this means this is a Tx here. And then the top one is our dielectric constants related to the SiO2 here. So that's a simple equations. Simple equations for the capacitance in the MOS cap. And right now we will start to interested in that if we start to apply the bias, consider for this MOS structure here. And the first one is we consider, we only focus on the part that we have the SiO2. So if we assume this is so first of all, we can try to rethink this structure as a two metal plate or certain two plate. It doesn't have to be metal plate, just a plate that you have the charge accumulated. So once we apply bias, for sure we have a charge here. And this is dielectric. We won't have any charge. But this is semiconductor, so it's supposed to also have the charge in this region. So therefore we can consider this MOS cap or this general capacitor is a two charge plates, and inside there's a insulator, which is a silicon dioxide. So therefore we redraw the previous MOS cap as a two charging plates here, and in between we have the SiO2, silicon dioxide. And of course, we have the dielectric constant, we have the distance, D here. And first one we discussed in the case where we start to apply the negative bias on top, which means so we apply the negative bias on top. So that means this is a positive bias and this is negative bias here. And once we apply negative bias here, we assume this one, we expect this also has a negative, and this will become the positive, right? So therefore in this case we will have the electric field in these directions here. So this is a case where we apply the negative bias here. And now if we assume, if we also consider, this is considering like you have the two plates, and in the place in between you have the SiO2. But now you consider back in our case, in our semiconductor. So we have the P-type semiconductor. And on top we have the dielectric. And on top we have the gate metal. So now we apply the negative bias here. So this is minus, this is positive, and this is our voltage here. Since right now we have the negative on top, and therefore we can expect this is a negative bias, and the negative bias will attract the positive charge, which will be the holes. So we can expect, because due to this negative bias, we will start to attract the positive holes here. And the electric field, this is because the electric field, E field, is in these directions here. And therefore, if we try to reconsider this plot again, we only consider the charge distribution. This is P-type, and we have the oxide here. Since we apply the negative bias, we start to attract the holes toward to the top. But right now, this is insulator. So ideally, the holes cannot overcome this insulator and move to the top. The holes will be only accumulated in this region. So as I say, the holes can be accumulated in this region. So that's why we call this as a there will be the large holes accumulation here. So that's why we call this as an accumulation layer of a holes. So once we apply the negative bias here, we start to attract the holes accumulation under the gate oxide. So an accumulation of holes at the oxide semiconductor junction corresponding to the positive charge on the bottom plate of the MOS capacitance, the positive charge. This is positive charge. And then this is an electric field, which will be equal to our voltage over our oxide thickness here. So that's the first operation. Okay, so that's the first case we apply the negative bias. And since for sure that we will not only satisfy with the negative bias, and the next part we will start to interested in apply the positive gate bias. So still the same. The idea is we consider as a p-type substrate. And now we still similar. We have the dielectric here, and we have the gate metal here. So the bottom one is a p substrate here, and we have the and right now we reverse our bias. So that means we apply the positive. So we have the positive bias. And the positive bias will lead into the positive here. And since we have the positive bias, and this positive bias will try to push our positive bias away, and that means we will try to push our holes away. So once our holes are being pushed away, what we actually left in the interface will be the negative charge. So that's the idea. That's the things will be happen once we apply the positive bias here. This positive bias will try to push the holes away, and what we left here is negative charge. This is one one source you can consider. Another is you apply the positive gate bias, for sure you will start to have the negative charge will try to attract it here, and therefore you can expect there's some negative charge in the interface as well. So these things are pretty consistent. So if the electric field penetrates the semiconductor, in this case, majority carrier holes will experience a force away from outside semiconductor interface. As the holes are pushed away from this interface, a negative space charge region is created. So we will have the negative space charge is created because of fixed ionized acceptor atoms here. The negative charge in the induced depletion region corresponding to the negative charge on the bottom plate. So this will become the bottom plate of the MOS capacitors. Okay, so that's the two cases that either we apply the positive bias, we will start to have the negative charge under the gate oxide, and we apply the negative bias, we start to have the positive charge under the gate oxide. So the next things we will be interested in how to use the Venn diagram to understand the case that we have already discussed. So the first one is we assume this is a p-type semiconductor. So we have the EC, EV, and our EF is close to the valence band. So that's EF. And on top of a semiconductor, we have the dielectric here. And then right now we assume our gate bias here on the metal is aligned with our Fermi energy in the semiconductor. So that means here and here are in the same certain position as a constant through the system here. So this is a condition where we call as a flat band. So the energy bands are flat. So that means this is a case there's no charge exists. In the semiconductor. Right, so because there's no band bending here, so if you still recall what you learned from the PN junction, what you learned from the Schottky junction, once there's a band bending, it always means that we start to have the charge, either for depletion or accumulation, whatever, it just start to have the charge there. But if this is flat, that means there's no charge in this semiconductor. So that's usually, we call this as a flat band here. And the first one we'll be interested in is just like a previous we have been already discussed. We first to consider the negative voltage applied. So once we have a negative voltage applied, now the band start have the band bending here. We have the students. This is our Fermi energy. But right now, since we apply the negative Vg, and the negative Vg in the band diagram is actually means that this will be increased here. So we can expect this one is become like here. And that means this will simultaneously to pull up, because the distance between here and here are the same, because we are using this, we consider same metal work function. And therefore, because the band is bending here, so we can start to expect the band is certain bending as well in the interface. And right now, if you look at close to this position between the EF and EV. So right now you found out that the EF is close to EV now. And what does that mean? That means we start to make this as more like the P-type, right? So P-type, it means that the EF is getting close to the EV. So P-type, that means we start to have the whole accumulation. So now you see that the what we try to illustrate here is pretty consistent to what we already schematically draw previous slide. So anyhow, under the negative bias, we always have the whole accumulation, and this can be seen from this band diagram. Also can be understood from this as well. So that's the case of a negative voltage applied. And next one we'll consider for the positive voltage applied. So again, under the positive voltage applied, so similarly can be expected right now under the positive voltage. This actually is pulling down. So the positive VG means here your metal work function is now lower than your Fermi energy in the semiconductor. So now we can also expect there's a band bending in our dielectric, and also there's a band bending in the semiconductor interface. So original, this is a p-type because our EF is close to EV. But right now at the interface, now our EF is close to EC now. So that means we start to induce negative space charge. So we can expect there's a negative space charge here with a depletion width. Certain discrete width XDT as shown here. So this band diagram is still very consistent with the idea shown here as well. And the next one we will start to look at in the case if we apply the sufficient large positive bias. So if we try to apply the sufficient larger bias here, actually our VG will become here. So we try to apply the sufficient larger, so then our VG is become at this region here, and therefore we can expect there's a huge band bending in the semiconductor as well. And the huge band bending means this interface will start to have even more band bending, and that means this one will be lower than this one, and this one, that means your EF right now exceed your EC. So once your EF exceeds EC, that means you start to have very strong electron inversion or strong electron generation at this interface. So right now we're going to draw in these things. And because right now we apply the sufficient large gate bias, and therefore our dielectric, the band bending in the dielectric here is shown in here. These are the band bending of the dielectric. And since right now it's very large, so we expect I should plot a little bit higher. So now we have very strong band bending here. This just because due to the drawing is not very precise, but ideally this should be somewhere like here. So anyhow, the idea is want to illustrate that once you have a large enough gate bias here, then your EF start to exceed your conduction band. That means you have very strong electrons in this region. So this is under the large. And that is our usually called as an inversion layer. So this, if you look at close to this band, that's actually band diagram in this interface. That's very similar to our degenerated semiconductor, right? So degenerated, that means our Fermi energy is already inside our conduction band. So that means this is the region where you have the N plus type. And the reason why you become the N plus type, that's because you start to have the electron inversion at this interface. So by applying sufficient large positive gate bias, we have inverted the service semiconductor from P-type. Original, this is P-type. Now this interface become like the N-type semiconductor. So we have created an inversion layer of electrons at the R-side semiconductor interface. So these three different cases actually is already include everything that we will have in the MOSFET, or everything we will have in the MOS capacitance. So in generally, when we discuss the transistor, we will consider the negative bias, positive bias, and very large positive bias. And then we can see that under different bias condition, there's a different type of the charges either being accumulated or either being inverted in the semiconductor interface. Similarly, we can consider the case which is N-type. This is a case for the N-type. So on the case of N-type semiconductor, now it's become, once we apply the positive bias here, you have the positive bias, and therefore you have negative charge inverted, negative charge accumulated here. And this is P-type, then we apply the negative bias here. So the ideas are very similar. So in the case of the N-type semiconductor, we apply the positive voltage here, then we will start to have the electrons accumulation at this interface. And now we start to moving to the slightly negative voltage here. Then we will start to have the space charge region. And the last one is we apply the large negative voltage. Then we start to have the inversion of the holes. So the ideas here just completely opposite compared to the p-type, and then the n-type is with accumulation of the electron with inverting of the holes here. Okay, so we will take a break for 10 minutes. We'll come back later. By the way, please put your homework here.
放到我看，不然反正你知道助教谁？对，好，不然你可以跟他说一下。好，谢谢。
Okay, so now first we already understand the physics, like the base concept. Once we have a different bias, and for sure that we will still move to some calculations, try to determine some critical numbers here. And the first one we'll be interested in is depletion layer thickness. But the calculation here is actually very similar to what we have been already done in the other structure we have already shown in the previous lectures here. So it should not be very complicated for everyone. So first of all, we consider this is a p-type substrate, and now we apply the positive gate bias here. So we will start to have this band bending where we already shown, and the phi s is the service potential. The service potential, and as we already know, under this case, we will start to have the induced space charge region. So the potential phi fp here is a difference in between the EFI and then the EF, and therefore we can calculate the phi fp is equal to this one, Vt natural log the doping in the p-type, which is Na over Ni, and the phi s here is called as a surface potential, and the space charge width now can be written in a form similar to the one-sided p-n junction. So that's why in the previous lecture we have been specifically mentioned this one-sided p-n junction, because we can use the same conclusion to the other cases like here. So therefore our depletion width xd is shown me here. And now this is, we start to apply a small gate bias. But if we start to continue to increase our gate bias, and therefore actually we will start to see the band bending is become more obvious than the previous one, and therefore we can have this one, the phi s can have the chance is equal to 2 phi fp here. So this condition is known as a threshold inversion point. And also the applied voltage to create this condition is known as a threshold voltage. And the concept for this threshold voltage is not only actually shown me here. Actually, this is really important when we consider the IV curve, especially the drain current versus the gate voltage here. And once we increase our gate bias, and once the gate bias start larger than our VTH, we can start to see the current is dramatically increased here. So this one is exactly the same like here. So now what we need to understand is from the IV curve we know there is a threshold voltage, but we need to understand from the Venn diagram point of view how do we determine the threshold voltage here. So electron concentration at the surface is an exponential function of the surface potential. So the surface potential might increase by few volts here, but which will change the electron concentration by orders of magnitude. So that means once we increase as a few volt here, actually this is exponential increase. So that means our concentration is actually increased very fast, as shown in this equation. So in this case, the space charge region has essentially reached a maximum width. This is because the once we have the condition beyond this one, and our Fermi energy is start to close to our conduction band, and therefore the surface charge here is actually increased exponentially, and whatever we additional bias apply, it will only reflect the charge in here and not influence the depletion width anymore. So that's why we will reach the maximum width as shown here. So this is a condition that we start to have very strong electron density in the channel, which is the densities in the MOSFET. So this is also the reason why beyond this condition we start to have a current, because right now our inversion density is increased very fast, and then rather than continue to increase our depletion width here. And similarly, we can do the similar things in the N-type substrate. So in the N-type substrate, we also have the phi Fn is equal to Vt natural log Nd over Ni here. And in here is also consider the phi s is equal to 2 phi fp. And above this condition, we start to have very strong hole here, and therefore we start to have the whole current here. So if you look at So this is a case that we start to consider as a P-channel MOSFET. So in the previous one, what we mentioned, if you look at the IV curve here, so we will have the once with VG is larger than VTH here. So this is the case. In the right hand side we have the current, and that's because we have the electrons inversion. And this is the case under the P-type substrate. And therefore, because this is P-type, but we have the electron inversion, so that's why we call this as an N-channel MOSFET. That's usually we call this as an NMOS. And also, similarly, if we consider in this case right now, we have the N substrate here. If we have the N substrate, so that means we will have the whole current here. Do you have any questions? Do you have any questions? No. Okay. So if right now we have the N substrate, and that means right now we have the whole inversion. So still the same. We can have the current output here. And also we can define this as a threshold voltage here. N substrate here. Because right now this is N substrate, so the current is contributed by the whole. So that's because we have the whole inversion here. And this is N substrate, but we have the whole, so that's we consider as a P-channel MOSFET. So sometimes we just call this as a PMOS. So that's a difference. So that's why we have to both discuss. In the case with P sub, we have the electron inversion. But right now we have the N sub, and therefore we have the whole inversion. And that's we call this as a PMOSFET. And the reason that we need to have the PMOS and NMOS together is because we actually hope to have the basic logic function that we usually call this as a CMOS. So the CMOS is a combination with one PMOS and one NMOS. So we have a PMOS, we have a NMOS here, and then we try to connect it with each other. So in this case, this is usually this kind of the structure we call as an inverter. So the inverter, that means the bottom one is a NMOS, the top one is a PMOS. The inverter, it means that if we have the signal input as a 1, it's mainly used for the logic function. So once we have the input signal as a 1, we have the output signal of the 0 here. So if we have the input signal of the 0, we have the output signal as a 1 here. So to realize this inverter, we usually need a pair of the PMOS and NMOS. That's why. So in most of the time, we have to consider these two things together. Now we all know that after the certain bias, as long as the bias is larger enough, the charge is mainly formation in here, and we won't have the increase of the further depletion width. So we will be very curious about how this charge density correlated to our bias, correlated to our service potential. So the service charge density can be calculated. Consider as here, N is equal to Ni exponential EF minus EFI over KT here. And therefore we can also consider the equation as shown in this one, EF phi FP plus the delta phi S here. And the delta phi S is mainly due to our applied bias. So once we apply the additional gate bias, that will induce additional service potential. So the phi S is related to our additional gate bias here. So this equation can be right as shown here. And finally, we can consider the NS is equal to this one. So that means our NS is correlate with our delta phi S as shown here. And the important thing is here, the inversion charge density is by a factor of 10 with a 6 millivolt increase. Of phi S. So that means we increase this for 6 millivolt. Actually, our NS will increase 10 times. And if you try to plot, this is NS versus phi S. So you can find out that this is 25 FP. This is 25 P plus 0.06. So that's a 60 millivolt. So the increase of this in the 60 millivolt. So delta phi S 60 millivolt, and that's leading to the 10 times higher for our service charge density here. And this is become very important because this becomes the bottleneck for our advanced semiconductor transistor. If you try to read further interpretation for these things, this actually is correlate with our current, which we can also plot as a log drain current versus our gate bias here, because we know the charge density is related to our current. Our phi s is related to our gate bias here. So this one suggests that actually, if we try to look at the gate current, gate voltage versus the drain current, we apply for the additional 60 millivolt, our current can be increased for 10 times. Therefore, if you try to calculate the slope here, we actually provide a specific name for this slope. That's we call as a subthreshold slope, or sometimes we call the swim or slope, which is the short name is we call the SS. So that means the limitation, the idea, the voltage you apply, try to turn on our transistor to have a high current, and then the most ideal case we can only achieve for 60 millivolt per decade. So that means whatever the material we change, ideally we cannot break this limitation, because our voltage applied here is always have to follow this 60 millivolt increase, as our 60 millivolt increase of bias will lead into 10 times of higher of our current density. And that's actually is a major challenge for the advanced technology. If you look at the advanced FinFET, advanced 2D transistor, advanced CFET, or whatever, people is always trying to look the technology that can minimize this slope. If we can make the transistor only 50 millivolt per decade or 40 millivolt per decade, that means our transistor can turn on faster. If this one is a 40 millivolt per decade, that means we only apply the 40 millivolt, but our current can increase 10 times. But however, in reality, it is a limitation here. So, therefore, if you try to look at some recent literature in the last 5 years, that's a really advanced semiconductor works that people always trying to find out whether there's a device that can break 6 millivolt per decade, that can have the substrate swing smaller than 6 millivolt per decade. Of course, there are some, but still under investigation. But if you look at the commercial device for the FinFET or even for the vertical transistor, the substrate swing is always between 60, it's always larger than 60, it's around like 70 to 80. Sometimes good is below, between the 60 and 70, but it's not possible to break this limitation. So that's become one of the challenges for right now technology. Okay, so then we also will be interested in how that the work function will be influenced in our MOS system. So this is a Venn diagram, the energy level in MOS system prior to the contact. So we have a Fermi level, we have work function here, we have the electrical affinity, and this is silicon dioxide. So we have very wide band gap, which is 9 electron volt here. And once we connect this one, this is under the case of the thermal equilibrium. So our Fermi energy is flat, but there's lots of things is going to exchange here. So you start to have a band bending you also will start to have a band bending here. So therefore, we will be interested for further to try to see that how this will be influenced for our band energy calculation. So first of all, the VOX0 here is a potential drop across the R side for zero applies gate voltage, but it is not necessarily zero because of difference between the phi m and electron affinity. And also we have this is a metal work function. So based on this band diagram here, we can have the following correlation, which is E phi m plus this one plus this one is equal to so this one plus this one will be equal to E phi this one electron affinity plus half of a band gap, but also still have to minus this one and plus this one. So that will be leading to the same amount or equal to these things here. And right now, if we try to minus E chi I at the same time, and therefore we have E phi m prime and therefore our phi s and we usually define this term as a phi n s, which is a metal semiconductor work function difference. So that's some calculations that we try to estimate the phi n s, which is a metal semiconductor work function difference. And also one more thing you have to know, this is under the thermal equilibrium, which means that also this is under the zero bias here. But under the zero bias, there's already the band here is not flat. So the band is not flat here. That means there's already the surface charge. Existed here. So when we consider MOS system, because due to the metal and also the semiconductor work function difference, even in the case we don't provide any bias here, there's already the band bending in the semiconductor interface. That means we already have the surface charge here. So that's why we had to estimate the phi and s, because the phi and s is a key that's in the end to leading to this band bending. So similarly, we can also estimate the phi and s in the n-type semiconductor. So as you see, in the case of the n-type semiconductor, we also still have the band bending, and our phi and s is equal to phi m minus So that's just some of the calculation that we want to estimate the work function between the metal and semiconductor. And also, one more small note here is sometimes we're not only use a metal gate, but sometimes we use degenerated dope polysilicon. So the reason is that because we want to have the very low resistance from the gate electrode. So for sure, the first choice can be the metal gate, and the second choice can be the dope polysilicon. So since this is dope polysilicon and this is degenerative, so that means our EF is already aligned with our conduction band. So that should be have very lower resistivity because this is a degenerated type, and also can be have the P plus poly here. So in terms of the gate, so the gate electrode, that means this is a gate metal put on top of the silicon dioxide. We usually have the two choices here. One is we use N plus or P plus polysilicon. Or another one is we just use a metal gate. So I would say right now is most of the case we use a metal in the most of the semiconductor device, but some of the cases we still use a polysilicon. So that's why we still need to mention that it is also possible to use a polysilicon as a low resistance electrode. Okay, so now we have to back to the one we have already mentioned related to the flat band voltage here. So the flat band voltage is defined as a applied gate voltage such that there's no band bending in the semiconductor. As a result, we don't have the space charge. So zero net space charge. So in the beginning, already mentioned that there is a condition that we call the flat band in the beginning of slide. But in here, we finally have the more accurate method to estimate the flat band voltage here. So as you know, when we calculate phi and S, we already understand that even there's no bias because of metal work functions difference between here, and there is a band bending, as shown me here. There's a band bending here. So if you try to make the band flat everywhere, we have to intentionally to add certain voltage here. So in here, we call the flat band voltage. And once we apply the flat band voltage, there's no band bending. So that means this is a zero net space charge at this region. So the equation showing here, if the gate voltage is applied, the potential drop across the R side and the surface potential will become like shown me here. And in the end, our VG is equal to Vox plus a phi S plus a phi NS here. This is because this one is equal to phi NS. And since after we apply the flat band voltage, there's a zero net charge in the semiconductor. So now if we look the charge distributions, we have the additional, this is a metal oxide and P substrate here. So right now we first assume that there's a certain of the fixed charge here, so that's we call as a QSS prime, which is we assume there's a equilibrium fixed charge, service charge. In the R side. Which is here. And now, because this is a zero net charge here, so that means the QM plumb here the charge, because we apply the flat band voltage, these two will be equal to 0, because in here we don't have the space charge, so these two will be equal to 0. And then the VRs can be calculated here, and also therefore this one will become in here. So in the flat band condition, the surface potential phi S is equal to 0, and this one in the end, this is in the flat band voltage, the phi S is equal to 0, and the Vox is equal to QSS prime over CX. So finally, our VF is equal to phi NS minus over Cx. So our flatband voltage here is related to our metal semiconductor work function and also the fixed service charge here. By the way, I know that if you are first time try to go through this, it's easy to get confused because it's not really understand how the logic behind. But you have to pay the attention, pay the patience, because in the end, once you try your hard to go through everything until the end, you will finally get a little bit sense that why this calculation have to work in this way. Because in here it's still the same. I think the most important is to understand the physics behind. You don't have to really struggle like why or how do we going to use this equation. We only use the equation in the homework and exam, but in reality, most of the time we only use the physics knowledge come from this equation, not really have to determine this precisely. But as being the course, we still have to go through this at least one time, and probably you'll get some sense. But if you in the end you forget all these things, that's still fine, but at least you should know that the flatband voltage is certainly related to your metal work function, it's related to your service fixed charge. And in the future, if you work on your own device, and suddenly you might have to optimize your flatband voltage, then you can start to consider that you have to choose a different metal, because that's related to the metal semiconductor work function. You have to certainly consider that how to reduce or increase your fixed charge, because that's also will in the end to influence your flatband voltage. Okay, so still actually our goal is still want to have the threshold voltage that can be estimated, because from the IV curve the most important one is the threshold voltage. So the threshold voltage is defined as the applied gate voltage that required to achieve the threshold inversion point. So we assume that there's an equilibrium oxide charge QSS and the positive charge on metal at the threshold hole is called QMT. So this is similar to what we have already shown. So this is a metal oxide and P-type substrate here, and we have the QSS prime here. So that's a QSS prime, and we also have a QNT here. QSS prime and QNT here. And right now, this is a case the service has been inverted, but also there's a certain depletion width here. So we will neglect the inversion layer charge at this threshold inversion point, because this is exactly at the threshold inversion point. So you will only have the maximum depletion width. So therefore, the overall charge balance is equal to this plus this one is equal to this one. And also this one is equal to the depletion width times your NA, and so that's equal to here. And the threshold voltage can be calculated as shown here. And at the threshold, we can define the threshold voltage, the gate bias is equal to the VTN, where VTN is the threshold voltage that start to create the inversion layer charge density. So the VTN is equal to VXT plus 2 phi FP and plus the phi NS. And because at this moment the phi S is equal to 2 phi FP. So this is something we have already mentioned, that the condition that we start to have an inversion, which is our phi S is equal to 2 phi FP. And also, right now is we apply the bias, so therefore the VG, once we apply bias, there will be a certain voltage drop inside the oxide and certain voltage drop inside the surface. So this is a voltage drop in oxide, and this is a voltage drop in surface. The threshold voltage VRT can be related to charge on the metal to the oxide capacitance, so therefore this is a 1 here. So the VST can be also considered by here. And finally, we can have this equation, which this one is exactly equal to flat band voltage here. So finally, we finish the part that it's a relative complicated and also sometimes difficult to catch what would be the logic behind for this calculation. But in the end, we finally have the equation to estimate the threshold voltage, which is related to the different term, that this is all the known terms that we know from the different place. But once we put all this together, we have the threshold voltage here. It's not easy to fully understand if you just follow this calculation. It's better if you have a question, you need to check the textbook. That's why the textbook is important. The textbook is the one that pretty clear to written everything in detail, especially the lost text. The text in the description text in the textbook is written very clearly to describe everything. You need to at least go through once, because if you give up in the middle, you will still very confused. You need to have a little bit passion to go through once until the end, and finally you will realize that why in the previous, like for example in this case, this is our goal, and now you will start to realize why we have to calculate the flat band voltage, why we have to consider this one, because that's all related to our threshold voltage here. Okay, so finally we finish those a little bit boring equation, but now we're back to the some of the content that will still have much physical interesting, because that still come from the physics point of view. So since we have already discussed a lot of the MOSFET, and one important characteristic for the MOSFET is we need to understand the capacitance voltage characteristic, which is usually we call as a CV characteristic. This is pretty important because CV is not only useful for the MOSFET, it's useful for all kinds of the semiconductor technology here. And in here, first of all, we consider the accumulation. Accumulation is something we already discussed, that we start to apply the negative bias here. So from the previous time, we already know that once we apply negative bias, we will have the whole accumulation. So this already something we already knew. But now we have to add something additional here. So still the same, we would prefer to use a charge distribution to understand the CV characteristic, where we have the metal, we have the oxide, we have the P substrate here. At this point, because we apply negative bias, so we can pretty sure that there's a negative charge at this point, which is minus Q here. But because we apply the negative charge, we start to have the charge balance here for sure. To maintain the charge neutrality, we can expect there's a positive charge formation at this point here. This is something we already know. But something additional is right now, if we consider the CV characteristic, we are not only consider the DC bias, we also have to consider the AC bias. So the DC bias is something if you try to plot the voltage versus a time. So first of all, we apply the constant DC. So DC is a bias, should be the constant all the time with respect to a time, if we consider that as a constant bias. But now, on top of DC, we have to also apply the AC signal. So we have the additional AC on top of this DC bias. So now we have this kind of the AC signal, and this AC signal actually in the end we have this one. This is dV. So that means there's a certain moment, this one is equal to V plus dV. And this moment is equal to V minus dV. And once we consider V plus dV, that actually will influence our charge. This also, because right now you have the DC and then you have some dynamic AC, so sometimes you have additional voltage, sometimes you have the reduction of voltage. And this additional or reduction of the voltage, that will create the charge difference here. So we can expect this sometime, for example, at this moment, voltage applied is V plus dV. So you have the additional decoupling. So this decoupling will reflect on here. And this decoupling also will induce additional decoupling in the substrate here. So therefore, we consider this small AC, that certainly change the charges between this plate and this plate, and that will create the capacitance in between. And this capacitance will be just exactly like the outside capacitance, because your charge is changed this place and this place, and that will lead into the formation of the capacitance with equal to this outside thickness, which is related to T-ox and exon ox. So therefore, at this moment, we will start to expect the capacitance is related to C-ox, which is equal to these two, equal to the exon ox over T-ox. So right now, if you try to plot your CV curve, your capacitance versus voltage, right now we are applying the negative bias, which will be certainly in this region here. And in this region, the capacitance under the accumulation mode is what we call the accumulation capacitance, CACC here. So the CACC here will be just exactly equal to C-ox, will be exactly equal to exon oxide over T-ox. So that's the first part of our CV curve here. So again, just illustrate the point. We apply negative bias. We already knew there is accumulation of the holes here. So that's something we already know. So if we plot the charge distribution, we have a negative charge here. For sure, we will induce a positive charge at this point. And that's because we have the whole accumulation. But right now, we consider not only for the DC, but we have to consider for the AC signal. So that means we apply the constant DC, and on top we have the dynamic AC signal here. And this dynamic AC will start to create the charge difference. This one, for example, at this point, you have the V plus dV, and that will create the additional decoupling here. And this decoupling will be reflected in this region. To maintain the charge neutrality, you also will reflect to here. And therefore, we have the charge change in this plate. And in this plate, for sure, we start to form the capacitance in between. And this capacitance just exactly equal to our outside capacitance. By the way, since we are a little bit behind schedule, so I will still want to spend a little bit more time to explain, probably like an additional 10 to 15 minutes. But if you need to leave earlier, you are feel free to leave now. Okay, so the next part is we are discussing for the depletion mode. That is the one we apply the small positive bias. So the concept is still very similar to previous one, but now once we apply the small positive bias here, first of all, let's look at the charge distribution. So we have the metal oxide and also the P-type substrate here. Right now we apply the small positive bias. For sure, first one, we induce the positive charge here. That's a. But right now, because this is under the small positive bias will form the depletion region. As you can see, this is our depletion region. So we will have the here. This is our depletion region. That's reached to our. This is XDT, which has a negative charge here. And similarly, right now we apply the AC bias. So AC bias will give us an additional charge. So we create the additional charge, dq prime here. And this additional bias will lead to the additional charge at this point. That's a dq prime here. So right now, if you consider the capacitance, then the capacitance not only equal to the oxide capacitance anymore. So we have still the same. We have the Cox here. And also we have to consider this additional depletion width. So that's a CSD prime here. So right now, our total capacitance in the depletion mode, which is equal to the capacitance of these two. So because this is a capacitance in series, so usually we write it in this way. This is capacitance in series. That's a. So now under the depletion mode, once we have a small positive bias, we start to have a depletion, and depletion will also have to consider the additional depletion capacitance here. So we can expect our CV curve now is changed. So in the previous, we have already shown this is our CACC, that's an accumulation capacitance. But because right now it's a depletion mode, we have the two capacitance in series. That means our capacitance is reduced. Once we have reduced, will become like in this way. So that's our C depletion. And we will reduce until one minima. That's our C mean here. So C mean is only happen once we have a maximum depletion width. So see, that's why in the previous, just maybe like 1 hour ago, we spent the effort to estimate the depletion width, because in the end, once we consider the CV, we also need to have the concept that's related to the maximum depletion width. Okay, so the last part is we start to increase more for our bias. So now we are interested in the large positive gate bias. And as you know, the conclusion is already something we know. Once we have enough gate bias, we start to invert our channel. We have the inversion electrons here. And let's look at how the CV characteristic will be look like. So again, if you look at the charge distribution here, we have the metal oxide and P substrate here. Right now we apply the large gate bias. That means we still have the quite a lot of the positive charge at this point. And in the previous depletion region, we already know that in the beginning you will have the depletion width will be formed here. But right now, because we apply the bias is larger enough, then you start to induce the inversion. You start to induce a very strong electron in the channel. So the part of the charge will be also induced in here. That's related to our channel electrons. And now if you consider the AC case, so we apply the additional AC, that will be dq plumb here, and that will create the additional dq plumb at this region, because right now whatever additional bias only influence the surface charge density here rather than the depletion width anymore, because the depletion width already reached the maximum here. So now if we look at the capacitance here, it's back to the oxide capacitance is between the metal and also the surface charge here. So now our capacitance here is exactly again equal to Cox. So if you try to plot the full curve for the CV curve here, so finally we can complete this CV curve. So first of all, we have a C accumulation, we have a C depletion reach to the minima, and again it moved to the inversion, you're back to the Cox again. So this is a point whether you have Cox. This is a CV, and in the left hand side is a CACC, and this is a C depletion, and we also have the C inversion here. In here, what we discuss is what we call the strong inversion. And actually in between the strong inversion and also the depletion region, there's a part of this one is we call the weak inversion. Okay, so that will be the last figure for this class. So we will end up the class today and see you next week.